We are revisiting the IPCC AR6 report now as a final approved version of the assessment synthesis of the assessment report AR6. The ones we had seen before, all the working group reports, they were called draft reports because they were not fully adopted by the parties that are signatories to the United Nations Framework Convention on Climate Change. So you can see that this one is called Adopted, just released in March 2023, and this is the synthesis report. This is the longer version. So I'm again just going to give a very brief introduction. It's a fairly long report, 85 pages, with lots of details, and there are some good details, so I'll try to make sure I capture all the important most salient point. The table of content basically gives an introduction. The second section looks at current status and trends, so we'll look at figures from that section and some headlines. Section 3 is on long-term climate development and futures, and section 4 is on near-term response in a changing climate. So it goes through the good, the bad, and the ugly, and the optimistic view of where we are headed. So section 2, let's start with this one. I already have the, Observed changes, impacts, and attribution. Human activities, principally through emissions of greenhouse gases, have unequivocally caused global warming, with global surface temperature reaching 1.1 degrees C above the 1850 to 1900 baseline, and this warming happened in 2011 to 2020. So that decadal warming is 1.1 degrees C. It's good to average over a decade so that the jumping around from year to year is not masquerading as a temporary warming or cooling. Global greenhouse gas emissions have continued to increase over the 2010 to 2019 period, with unequal historical and ongoing contributions arising from unsustainable energy use, land use change, lifestyles and patterns of consumption and production across regions, between and within countries, and between individuals. This is said with high confidence. So you can see the wording here is different than what we read before, and this is kind of what emerges after all the parties sit down and agree on all the specific wordings, which is a lot of debate, a lot of arguments, and finally something is accepted by all the parties. Human-caused climate change is already affecting many weather and climate extremes in every region across the globe. We have seen this already. This has led to widespread adverse impacts on food and water security, human health, and on economies and society, and related losses and damages to nature and people. Again, with high confidence, this can be said. Vulnerable communities who have historically contributed the least to current climate change are disproportionately affected, which is also something that can be said with high confidence. So these agreements on confidence intervals, confidence levels, are very critical for all the parties to agree on. The General Convention we have, which I missed somehow, is that these correspond to greenhouse gases, this symbol here. So increased emissions of greenhouse gases, GHGs, in gigaton CO2 equivalent per year. So the concentrations have been, and the emissions have been converted to CO2 equivalent using the global warming potential, as we know, especially methane, N2O, HFCs, and so on. So we are looking at the increases in greenhouse gases from the instrumental period beginning of the Industrial Revolution, even though this is 1850s, mostly because that's where the most reliable data starts from. CO2 is the biggest increase in fossil fuels the emissions. So CO2 from fossil fuels in industries is shown here, and CO2 from land use change and forestry, so LULCF is shown here in gray, which remains somewhat the same amount with some variations over time, whereas CO2 from fossil fuels in industry has monotonically increased and has accelerated over many periods along the way. And the non-CO2 emissions, which are involved in this CO2 equivalent per year. If we divide those into looking at the concentrations of greenhouse gases as they have increased rapidly since 1850. This is scaled to match their assessed contributions to warming over 1850 to 1900 to 2010 to 2019. So the decadal comparisons to the base period. So here you have nitrous oxide has gone now at 332 parts per billion of N2O. Methane has had ups and downs as well, but has generally increased to 1866 parts per billion for methane, and obviously these are measured in parts per billion, whereas CO2 is in parts per million, so it has gone from less than 300 to 410 ppm CO2 over this 2010 to 2019 period. We are now, of course, about 420, so every year we're increasing by 3 to 4 ppm. So you can see that this has gone from under 1000 ppb to over 1866 by now, and here under 300 to 332 ppb. You have to also remember this is about 25 times as powerful as CO2 as a greenhouse gas, and N2O is as powerful compared to CO2 by almost 200 times, so we have to worry about those as well. Human activities are responsible for global warming. With high confidence we can say that. So you can see here the global surface temperature has increased by 1.1 degrees C by 2011 to 2020 compared to 1850 to 1900. There's been ups and downs, but since about the 1940s we have basically tended to increase, and there was a flat period. There were some data issues which have been resolved, and there is always natural variability like volcanic eruptions and El Niños and AMOs, which affect the decade to decade, year to year variability, but each decade is warmer than the previous decade. So the warmest multi-century period in more than 100,000 years is in this range of 0.2 to 1, so we have crossed that threshold already. Humans are responsible. Observed warming is driven by emissions from human activities, with greenhouse gas warming partly masked by aerosol cooling over 2010 to 2011. That's again the change from the base period. So here is the observed warming, 1.1 degrees C, total influence right there, and well mixed greenhouse gases give us about 1.5 degrees C with a bit of an uncertainty there. Other human drivers like land use change can cool urbanization, can reduce albedo, and so on, and solar and volcanic drivers are about 0, and internal variability is quite large, but aerosol cooling is involved in this other human drivers as well, which brings the overall cooling down to 1.1 degrees C that we mentioned for 2010 to 2019 period, 2010 to 2011 to 2020 period. Emissions have grown in most regions but are distributed unevenly both in the present day and cumulatively since 1850. So historical cumulative net anthropogenic CO2 emissions per region, looking here in gigaton CO2 now, you are looking at time frames represented here from 1850 to 1990 to 2019, and we'll follow this up on the next slide. So North America obviously is high here, and here you have net CO2 from land use change and forestry. So that's the gray stuff here, and other greenhouse gas emissions, fossil fuel and industry, so CO2 from FFI, and all GHG emissions. So you can see Europe comes in here with 16%, Eastern Asia at 12%, Latin America and the Caribbean, and so on down to Southern Asia. International shipping and aviation are a significant contributor at 2%. That may not sound like much, but per capita that tends to have the biggest footprint as well. Net anthropogenic greenhouse gas emissions per capita and for total population per region in 2019. So this is over the period, and this for 2019. These are not easy to track, be very up to date, so you always peg a few years back. So greenhouse gas emissions in terms of CO2 equivalent per capita, so we keep switching between CO2 and CO2 equivalent as the data depends on the data availability and other factors. North America remains high at per capita just under 20. Australia is high. Eastern Europe and West Central Asia, Middle East, Eastern Asia, Latin America and the Caribbean, Europe here, South Asia, Southern Asia remains low, Africa remains higher in this calculation because of the net CO2 from land use change, etc. We know already that China is somewhere around 7 tons per person, India is at 3 tons per person per year, but these are misleading in the sense when you average over the whole country, the top 10% will be consuming just like the Western world, but the poor people are consuming much lower amounts, so we average and show a number that's lower. It still matters because the total emission, even though population is 3 times higher in India, let's say, than the US, the total emission is still lower. Okay. Global net anthropogenic greenhouse gas emissions by region over 1990 to 2019. So again, looking at CO2 equivalent per year in gigatons. So here we are in 1990, we were at 38 gigaton CO2 equivalent per year. We have now gone up to 59 gigaton CO2 equivalent. So here it really matters because the numbers you see as in the range of 30 to 40 are gigaton CO2, whereas if you add into methane and others, you jump to 59 gigaton CO2 equivalent, and that's in 2019. Okay, again, several regions: Eastern Asia, North America, Latin America, Caribbean, Southeast Asia and the Pacific, Africa, Southern Asia. Europe comes in here lower, but really Europeans keep calculating together and separately and so on. Eastern Europe and West Central Asia, Middle East, Australia, Japan, New Zealand, and international shipping and aviation, which we must continue to carry now separately as well. Regional indicators in 2019 and regional production versus consumption accounting for 2018. I won't go into all the details, but you can look at population in million persons in 2019 for each region. Gigaton per capita CO2 pegged to US dollar purchasing power parity, which is the economic term you can look up. We have discussed this elsewhere. That's pegged to 2017 US dollar. Net greenhouse gas emissions based on production basis. So when you produce something and export and it's consumed elsewhere, how do you account? Where is the emission attributed to? That matters as well. Gigaton, GHG emission intensity. So that's tons of CO2 equivalent per GDP, and GHG per capita. So you can always think of the Kaya identity again. So GDP, energy intensity, energies, CO2 intensity, and so on, to make all these things together. So CO2 from fossil fuel and industries in 2018 per person here, production-based emissions and consumption-based emissions, and you can see the numbers can be different. If you look, for example, North America, they are very close to each other, but if you look at Africa, it's different by about 30-40%, and also for Eastern Asia and so on. So it depends on who's importing, exporting, consuming, and so on and so forth. Change indicator, atmospheric water cycle. So we are now looking at the status and indicators again. So we are looking at atmospheric and water cycle, ocean, cryosphere, carbon cycle, land, climate, and synthesis. What are we looking at? Basically, confidence levels going from medium to virtually certain, and when it's in black, it's a fact. Okay, so this matters how you think about it. So you're looking at observed change and human contribution assessment. So it's kind of an attribution exercise. So if you look at atmosphere and water cycle, for example, warming of global mean surface temperature, surface air temperature since 1850 to 1900. Observed change assessment, it's a fact. Human contributions are a fact. Likely range being uncertain, so human contribution from 0.8 to 1.3 degrees C, encompassing very likely range of observed warming of 0.9 to 1.2 degrees C. In the ocean, you have ocean heat content increase since the 1970s is virtually certain, and the main driver is in this scale extremely likely. Okay, there are salinity changes and global mean sea level rise, which is a fact with very likely contribution coming from humans. Under atmosphere and water cycle, you also have warming of the troposphere, cooling of the lower stratosphere, large-scale precipitation and upper tropospheric humidity changes, expansion of the zonal mean Hadley cell circulation since the 1980s, but you can see here the confidences drop quite a bit, and the northern and southern hemisphere responses are different based on the various dynamic and human contributions, land size versus ocean size, etc. In cryosphere, Arctic sea ice loss, again very likely with human contribution being the main driver. Reduction in northern hemisphere springtime snow cover, again very likely. Greenland ice sheet mass loss, virtually certain, but there is limited evidence and medium agreement on human influence. Retreat of glaciers, again very likely, and humans being the main driver. In carbon cycle, you have increased amplitude of the seasonal cycle of atmospheric CO2 since the early 1960s. Likely and high confidence, humans being main driver, is also said with medium confidence. Acidification of the global surface ocean, virtually certain with humans being main drivers. And land climate, mean surface air temperature over land about 40% larger than global mean warming. Land heat capacity is low and warms faster, and you have a lot of land use changes contributing to it. So the albedo changes more than compensate for the human influence. So this is a fact, and the human drivers being the main driver is very likely. In synthesis, warming of the global climate system since pre-industrial times is a fact, and humans are responsible is also a fact. Moving forward, climate change has impacted human and natural systems across the world, with those who have generally least contributed to climate change being most vulnerable. This kind of depiction we had seen already in the draft report. So here we are looking at synthesis of assessment of observed change in hot extremes, heavy precipitation, and drought, and confidence in human contribution to the observed changes in the world's regions. So here we go from the dimension of risk, which is got hazard, exposure, vulnerability, response, and so on, which we have addressed elsewhere. The type of observed change since 1950s, there is either increase, decrease, limited data, or literature, so no studies reported. Remember, IPCC tends to synthesize published reports and data, and where there are bars, there is low agreement in the type of change, so it's not very high confidence there. Confidence in human contribution goes from high to low, so 3 dots there. So if you look at hot extremes, pretty much everywhere high confidence, and pretty much everywhere increase, except there are places where there is no data and there is no agreement. If you look at South Asia, South and Southern Asia here, you see there is high confidence in hot extremes, and this is really becoming very obvious in terms of duration, intensity, and frequency of heat waves, and this is something to really watch out for, because they are the most vulnerable and they are not historically the contributors, and the forcing often comes from elsewhere, remote forcing, so adaptation strategies have to worry about those. These are all the names of the regions, which I'm not going to read, but you can guess by looking at the location on the map what they are. Looking at heavy precipitation, again going from temperature to precipitation, you immediately see the problem with the models. Models can do temperature very well, and that too at a regional scale, not at a local scale. Precipitation tends to be problematic for models because of various dynamic issues which we have discussed elsewhere. So lots of places where there is no agreement, or there is limited data or literature, but nonetheless there are places where you can see there are increases. So these bluish colors are all increases. So Southeast Asia here, the confidence limit is low in terms of the impact or changes in heavy precipitation, but people feel the effect, so you have to consider it as risk and do what you have to, knowing that the risks have been increasing. Agricultural and ecological droughts, again similar, low confidence, and many places no agreement or no data, but mostly there are increases in many places as well, which we have seen elsewhere. This is a nice graphic which shows that the 2019 emissions per capita of the 118 nations in tons of CO2 on this axis, and here is the relative average national vulnerability per capita by global indices, which are from the World Resource Institute and Inform from 2019. And the main message is that the most vulnerable countries generally have lower emissions per capita. The higher emitters, rich countries, have lower vulnerabilities, but now it's clear each summer and winter there are extreme events which are hammering even rich countries, so we are all now becoming more and more vulnerable. The vulnerability goes up here at the end for some high emitters, for example. Okay, so we're looking at the vulnerability aspect of the dimension of risk here. So vulnerability is assessed on national data. Vulnerability differs between and within countries and is exacerbated by inequities and marginalization. Many more details here. Again, we have discussed these before, so I won't kind of skip through these. Observed impacts and related losses and damages of climate change. Loss and damage is the word now accepted and used. There has been an agreement in the last COP showing that there may be some mechanism to compensate for the countries which got hammered by climate change, like the Pakistan floods, so helping them financially to cope and adapt as well. Okay, so rich countries hesitated on that for a long time because that would amount to admitting guilt for global warming, a causal agency for global warming, which they don't want to do because of legal ramifications that could come down the pipe and so on. So looking at increased climate impacts on human systems with adverse impacts on ecosystems, climate change driven changes observed, no assessment of impact direction when it's gray. Confidence of attribution again is either not assessed or evidence is limited, and when it's 3 dots it's high or very high. So you're looking at human systems, ecosystems. So here you have water availability and food production with physical water availability, agricultural crop production, and so on. Fisheries, eels, and aquaculture are also included here for various regions and global. Health and well-being, cities and settlements, and ecosystems. You have changes in ecosystem structure, species, range shifts, and changes in seasonal timing or phenology, early arrival of the spring, late arrival of the winter, and so on and so forth, which affect things in terms of rainfall distributions, insect infestations, migration of species, etc. Right? So a lot of reds here. So human systems being affected with mostly high confidence 3 dots. There are some where they are not assessed in some regions and so on, and you can see the various ecosystems in terms of terrestrial, freshwater, and ocean. I want to wrap up section 2 in one podcast, but maybe it'll get too long, so let me cut this here because it's getting too long. So let's come back and look at responses undertaken to date in the next podcast. Okay, so let me stop this here for now. It's already over 22, it's already 23 minutes. Okay.